Greetings everyone, we're going to be talking about motion in 2 dimensions. To warm up for this, we're going to be talking about vectors in 2 dimensions. So what this means is that, say that we walked 3 blocks to the east, and then we walked 4 blocks to the north, so something like this. Then what is our displacement? So we could draw our displacement vector something like this and call this A. So there's a couple ways that we could represent the vector A in 2 dimensions. One is just by splitting it up into x and y components. So it'd be like 3 x hat plus 4 y hat. And this is about the same way that we got there. We said 3 to the east, right? Plus 4 to the north. And east and north are orthogonal directions. What we mean by orthogonal is that these are 2 different vectors that are perpendicular to each other, like x and y. So this is called orthogonal. And the nice thing about orthogonal is that if we have a vector in the x direction, we can just add it to itself without bothering anything about the y direction. And we're going to see that on the next slide, how to add these vectors in 2 dimensions. So the other way that we could represent A is given its magnitude and then the direction that it's at. So plus some theta. So the way that we could say that is the magnitude of A. So let's go ahead and work this out. So the magnitude of A is going to be 3 squared plus 4 squared. This is just Pythagorean theorem. And so you're going to get 5 meters. Maybe these are all meters. So then a vector could be 5 meters at, now we need to talk about what this theta is. So this theta we could be measuring north of east or counterclockwise measured from the plus x direction. These are all fine ways of talking about this. But the angle theta here, so let me just redraw this. So this is 4 and this is 3. This is theta. Then you could note that tangent theta is 4 over 3. So that means that tangent theta is going to be the arctangent of 4 over 3. And when you work that out, I think you're going to get 53 degrees, something like this. So we could say that A is 5 meters at 53 degrees measured from the counterclockwise direction from the plus x axis, or 53 degrees north of east. These are all fine ways of talking about these vectors. In general, it's going to be easier to use this kind of notation, 3x hat plus 4y hat. So let's add some vectors. Here we have A plus B. And so let's work out what this is. So here, A plus B, what we're going to do is pretty much just add all the x components and then add all the y components. So here we're going to get 3 plus 4 x hat plus 4 plus 3 y hat. And so what you're going to end up with is 7x hat plus 7y hat. So that wasn't so hard. So let's try a different example. Let's try A plus B plus C. These are all vectors that we need to add together. So we could kind of draw this out and then show kind of what we're talking about here. So A is going to be 2, and then now we're going to go up to 9, something like this. So A is going to be something like this. So this guy is A. And then let's switch colors. So B is going to be 4 and then minus 1. So maybe be something like this. So this guy's B. And then C is going to be -6 and then -7. So I'm going to end up with something like this. C will end up being like this. So then the result of all of these is going to be this tiny little vector like this. We're going to call that guy D. So let's work out what D is. So the way that we're adding vectors is that we connect them head to tail. What I mean by head to tail is that, say if we had A like this, then B needs to start at, his tail needs to start at A's head, and then you're going to end up with something like this. Then the result of these two is, starting from the tail of A, go all the way, pretty much follow these arrows, all the way to where they end up with, and then this is going to be our result. So that would be kind of what D is doing here. So A plus B plus C is going to be 2 plus 4 minus 6 x hat plus 9 minus 1 minus 7 y hat. And what you're going to end up with is 0 x hat plus 1 y hat. Or just 1 y hat. So now we're kind of ready to talk about kinematics and trajectories in 2 dimensions. So the very first thing to do is to draw a problem. And we're going to be doing that with the next couple of examples. And we need to label our origin and which way are positive x and y. Then we're going to write out all that we know and all that we'd like to know and make a table kind of like this. So x and y, and then we're going to say what's the x distance that we have, what's our initial x velocity, what's our final x velocity, what's our acceleration in x, and what's the time. And do the same thing for y. Let's watch a video. So in this video, Dr. Andreessen kicked a football, and we're going to write out how far he kicked the football in this x direction, and then use the time that it took that the ball was in the air. So going from this point, about 1.3 seconds, all the way to when the ball landed on the ground. And then calculate this x distance, and then from that what we're going to do is find out how fast was the ball moving right when it was kicked off of his foot. So we found out that the x distance, using these yard markers as a reference, was about 13 meters, and the total flight time was about 3.2 seconds. So let's go ahead and draw out our coordinate system. So here is the initial velocity of the ball. But this is a two-dimensional vector. It has components in both this x direction and in this y direction. So we need to split v into two different components, into a vx initial and a vy initial. So let's write out our xy table. So our x distance was 13 meters. Our vx initial, well, that's what we want to find out. Vx final, that's going to be the same thing. Ax is 0. And the time that it took was this 3.2 seconds. So y distance. So this ball follows a trajectory like this, something like this, and then lands somewhere over there. So the initial and final y, both y initial is 0 and y final is 0. So y is actually 0. So vy initial, that's what we want to know. Vy final, we don't really care about that. Ay is going to be minus 9.81 meters per second squared. So here is our acceleration due to gravity. It's pointing downwards and our y is pointing up, so that's why this is negative here. And then t is going to be also 3.2 seconds. You'll find out that t actually links x and y together, and it'll be quite useful in order to relate what we found out in x to what we found out in y, as this t is going to help. So in here we have more unknowns in this y direction because we have this vy final. So let's start off with the x direction. X is usually easier. So x is equal to 1/2 v initial x plus v final x times t. And these two guys are both the same thing. So this amounts to x over t is going to be just vx, which when we plug in 13 and 3.2, we're going to get 4.06 meters per second. And this is our x part of this triangle right here, of this v that we're wanting to find. This vx is going to be 4 meters per second. So now let's try to find our y velocity. So y is equal to y naught plus v initial y t plus 1/2 a t squared. And so both of these are zeros, so we really just get v initial y times t is equal to plus 1/2 minus 9.8 t squared. So now we know what this t is. This t is just 3.2, so we're really just solving for this vy. So this vy is going to be equal to 9.8 all over 2 times t squared, and then we actually divide by a t, so this is just t. And when we plug this in, we're going to get about 16 meters per second. When we want to find out this v up here, what we need to do to find the speed is we're going to do Pythagorean theorem, 16 squared plus 4 squared, 16.5 meters per second. So, in general, there's a whole bunch of projectile problems that we could work out, but the easiest kind are these y equals 0. So you're going to start off at some y equals 0, here's y direction, and then you land back where you started from. And so then you can say, if we know the angle that we kick at, so that angle is this right here. So this is v, this is vy, this is vx, so this angle theta. If we know the angle that we kick, how far does this projectile go? So just from this we can see that vx is going to be v cosine theta and vy is going to be v sine theta. So how far does it go? So this is, we're looking for actually x, how far that goes. So when we make out this table, we want to find this x. And so vx initial, well, we know that. That's just this v cosine theta. And then ax is 0, and then t, well, we don't know that. So y is actually going to end up being 0 because we end up back where we started. The y initial is just v sine theta. The y final, we don't care about that guy. Ay is our minus 9.8 meters per second squared. And then t is going to be, well, we don't know. And so in this case, you're going to see that we're going to solve for this t and then end up plugging it back into this for x to solve for the range that the projectile goes. So we're going to use y is equal to vy initial t plus 1/2 minus 9.8 t squared. And so this y is actually just 0. So one of these roots, this is a quadratic, we're going to be solving for t. One of these roots is t equals 0, and we don't really care about that. So what I'm going to do is bring this guy to the other side, and so we're going to get 9.8 t squared over 2 is going to be equal to v sine theta t. And you can see right away that one of these roots is 0, that t cancels out with this t, and so we're going to end up with, we're really just looking for this t, so that tells us that t is equal to 2v sine theta all over g. That's the 9.8. So this is our t, and what we're going to do is plug it back into this side. So we know that x is equal to v times t, because there's no acceleration there. So this vx is really just v cosine theta, and now times t is 2v sine theta all over g. So we can simplify this a little bit and get 2v squared cosine theta sine theta all over g. And now we can use a half angle formula to kind of make this a little prettier result. So cosine theta sine theta times 2 is really just sine of 2 theta. So we're going to end up with v squared sine 2 theta over g. So here we found out that x is going to be equal to v squared sine 2 theta all over g. And this is if, it lands back where it started, back at y equals 0. So you can see here is a couple of trajectory plots that we had. And I've made a couple plots at different thetas. So one thing that you'll notice right away is that this 45 did the best. It got the most distance, this x. Using the same velocity, we just shot it off our projectile at a different angle. So if you want to shoot the furthest, ignoring air resistance, then shoot at a 45-degree angle. It's going to go the furthest. So here's just another plot. Basically, it's just a sine of 2 theta, and I plugged in v equals 10. That doesn't really matter. But what you'll see is that the best that you can do is this 45 degrees right here. So another thing to notice is that if you kick it at 30, or if you kick the ball at 60, they go the same distance. Or if you kick the ball at 20 and kick the ball at 70, they end up going the same distance. So the same distance away from 45 ends up getting you the same distance, basically. And why that is this sine 2 theta in here. So let's work out one more problem, and in this case, y final is not going to be 0. So we're basically starting at one height, and we're going to end up at another one. So here we're going to throw a stone off a cliff that's 10 meters high. We give it some initial velocity and throw it at some angle. So we need to figure out the time that it takes to reach the ground, and then we're going to use that time in order to find out how far did it go. So I've already plotted it here. We know it's going to take about 15, but let's do the math. So in this picture, we are throwing the ball at some angle. That color is no good. And so there's initial x velocity, and then an initial y velocity, and then there's our theta. So if we want to find Vx initial, that's just going to be this 10 meters times cosine of 53 degrees. And Vy initial is 10 times sine of this 53 degrees. So let's make our table. All right. So x, well, that's what we want to find ultimately in part B. Then we have Vxi, well, we know that guy. Vx final, we also know that guy, that's just this. AX is 0 again, and then T, we also want to find that. So we basically don't have much that we know in this X direction. We need to find T in order to get the rest. Y is actually going to be, well, Y initial is 10, but Y final is going to be 0. So this Y initial is 10. We need to know both of these guys. So Vy initial is going to be our 10 sine theta. And then Vy final is going to be, well, we don't know that. Ay is going to be minus 9.8 meters per second squared. And then T is going to be, we need to find that. So for Y we have Y equals Y naught plus the initial Y times T plus 1/2 a T squared. So here our Y final is going to be 0 and our Y initial is going to be 10 plus the initial Y, so that's 10 meters per second times sine 53 degrees times T plus 1/2 minus 9.8, T squared. And what you'll notice is that this is a quadratic, and we can't just say T equals 0 because we have this 10 here. So we have to plug this into the quadratic formula. So T is going to be equal to minus B plus or minus square root of B squared minus 4AC over 2A. And we're going to find out that we're going to get 2, because we have plus or minus quadratic. So we're going to get 2 times. One is minus 0.829, and the other one is 2.457 seconds. So we have 2 times at which Y is going to be equal to 0, because this is a parabola. So one of the times is here, and the other time is this time back here. So this time will be this minus 8.3, and then this time will be the 2.4. So then we can use this 2.4, so this is our time that it took to reach the ground, so this is 2.46 seconds. And then now we can just use x equals the initial x t, and we can find out that it's going to be about 14.8 meters.